Alright, so we're ready to start with Covnets because we know now how a signal is presented, we know what convolution is. So we're gonna basically convolve this image with a filter. We call this a filter F. Yeah. Here you have your image, assume the image is of a cat. And then you're going to slide this filter over that image, in that direction and in that direction. Yeah. And the filter in this case, and this is a two-dimensional case, here we have 9 weights. Yeah. And the goal of training the network is to find these 9 weights as to the predicted image is as close as possible to the truth, which is a cat. Yeah. So that's basically it. You train the weights and you make sure that in this case it's going to be a log loss because it's a classification problem. So you minimize the log loss. Alright, so filter on an image, and at the end we take the ReLU of that convolution. Yeah? We often gonna use ReLU. As I mentioned before, the interesting thing about ReLU is that if this is Z and this is Y, yeah, your ReLU is actually going like this. Yeah? So it is 0 for Z negative, and it has a constant gradient when Z is positive. Now remember, what we did not want to have was this type of function, because here your gradient saturates. Yeah, so you won't have this in a ReLU. Alright, so let's take this off again. Yeah. So now we're going to look a little bit more in detail on how we apply convolution. How does it mathematically work? Well, therefore I have an image here which is a 6 by 6 image, and you see the 3 first columns I put a 10 in each cell, and the last 3 columns I put 0. Now the higher the number, the brighter the spot. So if you would have sort of brightness representation, then you would have a darker view here as we would have here. And we're going to convolve that by a 3 by 3 filter, and this filter is going to detect vertical edges. Alright, so here again 1 is brighter, this is medium, and -1 is dark. So now we're going to convolve these two. Yeah? So how does it work? Well, the first thing I do is I place this filter in the top left corner. So here I will see 1, 0, -1. Yeah? 1, 0, -1, 1, 0, -1. So if I do 10 times 1 is 10, plus 10 times 0 is 0, 10 plus 0 is 0, and then minus 10 here. 10 minus 10 is 0. Yeah, so the first row with this first row gives 0. And since the rows are the same, this will give 3 times 0. And 0 plus 0 plus 0 is all 0. So your first element here is going to be a 0. Yeah? And that is basically the convolution of these 3. Yeah? So this filter upon these 3 columns and rows. Alright, so the next thing we need to do is we need to slide the window. Yeah? And a slide is called a stride. I've defined it here. What is striding? It's the number of pixels you're going to move in a spatial direction. And we call it S, striding S. Yeah? Although you can do more than one stride, you can use striding S equal to 2, it's not that often used. Yeah. The default is going to be 1, and we'll be using 1 most of the time. So we have now this element here. So this is your feature activation map. It's actually before you take the reloop, yeah? Because the reloop could actually change these numbers. Okay. So then what we do, we move 1. Assume stride is 1. So you move 1 to this direction. So this is going to be the orange one. Yeah, so this is going to be the area where you look at. So you look here, 10 times 1 is 10. This is here, 10 times 0 is 0. So 10, 0. And then 0 times minus 1 is also 0. So here we have 10, right? From the 10 times 1 we have 10, all the rest is 0. And we have it 3 times. So the outcome is going to be 30. Okay? So you can slide 1 more. If you slide 1 more, then you're going to work in this one. But here again, this is going to be 0 if you convolve with these 2 columns. And this is going to be 10 times 1 is 10, and I have this 3 times. So this is also going to be 30. Yeah? And if I move the filter on the last 3, it's all going to be 0. Yeah? Okay? So now what you do is you start all over again, but you move 1 stride in this direction. Yeah? So you look at these 3 here in your second pass, and then in your third pass you look at this, and in your last pass you look at the final 3. Okay, so since everything is the same, we can basically duplicate all this. Yeah? It's going to be 0, 0, 0, 30, 30, 30, 30, and here all zeros. Yeah, why is this a vertical edge detection filter? Well, it's pretty obvious here. The outcome is gonna be that you're gonna have darker spots where the zeros are, and in the middle you're gonna have the 30, so that's gonna be a bright spot. Yeah. So this filter here you could see as bright, a little bit darker, and more dark. Alright, so I just wanted to show you how this filtering works. In machine learning, we're going to try to determine that filter, or the weights. There's going to be 9 weights, and we're going to choose the weights as such that the predicted y is as close as possible to the true y. Alright, so there's of course 2 issues with all this. Yeah? Issue number 1, as you can imagine, is that this upper right pixel here, yeah, all these squares are pixel. This upper right pixel here is going to be addressed only once by the filter. Whereas if you take a pixel here in the middle, it will be addressed many times. Yeah? So you lose a little bit of information, especially when it comes to the edges of the image. Another issue you have is that you've seen that we started with a 6x6 image. When we convolve it with a 3x3 filter, our output is going to be 4x4. Yeah, so your output is going to shrink. Yeah. Every time you convolve, and remember, you can have 100 layers. Yeah. So one solution to avoid this is to use what we call zero padding. And what is zero padding? Well, you're just going to add zeros all over the place here at the edges. And now in this case, if you calculate the dimension of the output here, it's going to be 6 by 6, which is the same as the input. Yeah. So here we now have an 8 by 8 image because we zero padded. Okay. And so what's the outcome of the output image? It's n, it's the size of the image, minus f is the filter. So we have 8 minus 3 is 5, plus 1 is 6. Yeah? So we have a 6 by 6 output. Striding, we have seen, is the number of steps you take every time you move your filter in a certain spatial direction. So this is the formula per spatial direction. The output or the length of your output image is the length of your input image minus the length of the filter or the size of the filter, and then plus 2p, and p is the number of zeros padded. And so you have actually plus 1 here, but you have also plus 1 here. So that's why we have 2p. We divide by the stride. In most cases it's 1, and then we add 1. Yeah. All right. Now that we know a little bit more about the definition and how the mechanics work, let's go a little bit deeper in the architecture.